We have a lot to get through today, so I'd like to introduce Professor Eugene to give us an opening remarks about what's at stake and where we can go from here in Africa and around the world. Thank you, Professor.
Hello, everyone. I'd like to thank the organizers for not just for inviting me, but putting this wonderful show where all the main messages have already been delivered. That's a good news. Less good news is that I'm an engineer, so I'll have to show you some numbers. So be prepared for that. Is this the... Okay. So to set the stage, you came to this event, so I'm assuming that you're already fans of nuclear power. Nevertheless, it's worthwhile going a little bit through the main features. It's not a surprise to anyone, but just to register that. So nuclear power is low carbon energy source, so worth stating that. I'm sure this is not a surprise to anyone. It has a tiny footprint, so enormous amount of electricity can be generated in a smallest area without interfering with nature and other human activities. It's predictable and will provide power when you need it, yet flexible when you want to accommodate fluctuations in power demand. Fuel costs are trivial. This may be a surprise to some of you, but for all practical purposes, fuel is not just abundant, but it's also extraordinarily cheap. So the cost of nuclear electricity is in capital cost of the power plant, not in the fuel. So, and has already been alluded in previous session, the costs of spent fuel management are also surprisingly small, and it is surprisingly safe proposition. So, however, everyone was waiting for however, it does have challenges. So arguably the biggest challenge of nuclear power is costs, of course. So this is where small modular reactors are coming in. So long construction times as a corollary of this. Heavy regulations have been mentioned. Despite the actual small cost of fuel and waste management, the public thinks it's very dangerous and the fuel is limited and very hard to manage. So traditionally, reactors were built to be larger and larger in pursuit of an economy of scale. So let's explore that concept a little bit. So what you see here is a marvel of engineering. This is a French / German design called EPR, which we're building in the UK at Hinkley Point C and hopefully soon at Sizewell. So numbers here are actually not that important, but the shape of that curve is important. It basically tells you that the bigger the power plant is, the cheaper it becomes. So this comes from the fact that there are multiple things you have to do that costs that you have to incur regardless of the size of the plant, like qualification of the site or building a road that leads towards that site. You have to incur that cost regardless of the size of the power plant. Another thing I want you to note is that this curve is non-linear, so it kind of takes off at really small power sizes. So why would we contemplate smaller reactors and hoping that they will be any cheaper? So let's explore that a little bit. So one of the things that have been talked about previously is a shocking realization that cost of nuclear, because they are mostly costs of capital, hugely depend on financing. So this is Hinkley Point C, but other large reactors in the West have similar, or you can have similar observations. So the green piece of the pie is the interest on your loan or servicing the debt for the construction, which tells you what are the most straightforward ways of reducing the cost of nuclear is to have more creative financing with or without government support. Another observation which was also voiced is the fact that the cost of hardware, all the equipment and pipes and valves and pumps and heat exchangers, or the reactor pressure vessel and so forth, they are relatively small. They're roughly a quarter of total costs. So where are those costs? And why do they vary so much across the world? So two particular colors I want you to note here. One is productivity of labor in on-site construction, and another one so-called indirect costs. Another way of saying this is bureaucracy or administrative burden of some people do the welding and concrete pouring, but 5 people standing nearby and checking that this is done appropriately. Is this the most optimal way of doing this? I don't know. There are obviously other success stories. What you see here is comparison of nuclear costs in North America and Europe versus rest of the world, with no cutting corners here. These are the same technologies being compared. So bureaucracy and cost of capital are the two obvious things to watch. And because you need to borrow so much money for so long, why don't we try to borrow less money for a smaller project that gives you returns sooner? So that makes your interest payments smaller. So I thought small modular reactors idea go back to sort of early 2000s. This is produced by Westinghouse in the US. This curve, again, the familiar economy of scale, but I dug a bit deeper and discovered this paper from 1980s published in British Nuclear Society Transactions or Journal of British Nuclear Society, which argues exact same thing. So by going smaller, less money to borrow, there's higher certainty for project development, but also an opportunity to move expensive labor on site to cheaper labor in factories where you have better control, more opportunities for learning and more opportunities for standardization and quality control. So all these ideas have been around for a while, and now we are, as sort of a global nuclear industry, are trying to take advantage of those. So one of the key things in that pursuit is how modularizable the designs are. So absolutely key thing is the so-called degree of modularization. So the more of the power plant components you can move from expensive site to cheap factory, the better. And it turns out the smaller the size, the more modules you can, or the larger the degree of modularization that you can achieve. So as you can see here, the larger that degree, the lower the curve of economy of scale becomes, and at some point it becomes nearly flat. So your cost of nuclear construction becomes sort of insensitive of the power or the size of the power plant. So if you apply all these concepts in chain, if you build small reactors the same way you build large reactors with lots of on-site labor, the first 2 bars compare one large reactor, which is shorter bar, and if you build that same capacity with several chunks of smaller size, but build in the same way, economy of scale tells you that cost will be much higher. Not double, but much higher. However, exploiting these opportunities for modularization, learning, standardization, not just manufacturing processes, but also regulatory processes also has been said before, then applying those, you can reduce the cost to something that is actually even smaller than the large reactor, but inaccessible in a way, in the same way if you build something like an NEPR, which is sort of the standard way of doing things, at least in the West. So I want to leave you with a few key messages here. So first of all, SMRs as an economic proposition is a very attractive concept, and I'm very excited about this, and I think we all should be. Let's make a good example here in Africa pursuing this. So, as I said, modularization is the key. It can be cost competitive with large light water reactors, but it will require very highly optimized supply chain, which enables learning and economy of mass production to compensate for negative economy of scale. So again, that was said in the previous panel, or fireside chat, that it may come as there's a slight tension here with the desire to bring jobs and localize as much of those construction or manufacturing activities locally. Where this sweet spot is, I don't know, but this is something for us to explore. We talked about financing costs and necessity of deploying these power plants on a large scale. So for the learning to materialize, for manifest itself, it needs a reasonable volume of production. You cannot learn from two plants. It needs to be 20 or more to make the factory transition to factory manufacturing worthwhile. Couple words about microreactors, and I'm finishing here. So these are at the very extreme of the economy of scale curve. So they will really struggle to compete with large reactors, but they don't have to be. So these are designed or intended for off-grid operations, such as mining or islands or hard-to-get-to areas where the local construction can be absolutely minimized. So from bringing the power plant on site to electricity flowing out, that time shrinks enormously, and you don't have all the expensive grid connection costs as well, so it can be economic. And it can be also decommissioned and taken away. So I do see bright future for microreactors. Just finishing and re-emphasize, or cannot emphasize more, the importance of not just infrastructure, but human infrastructure. So this is arguably the longest lead item in any project. So good people or competence that is being brought on a large scale. So as we heard today, the market or the demand for electricity is unlimited in Africa, essentially. Whatever we as an industry can deliver, it will be happily taken away, but it cannot happen without thinking about human infrastructure, and we at Cambridge are working towards that. So I hope this sets the stage. You know what to ask our panelists, and I'll turn it back to Ryan. Thank you very much, and apologies for slight delay.
Thank you, Professor.